On forces and stresses in a footing. In this video, you will learn about footings, their purpose and nature in a foundation, their structural behavior, and reinforcement layout. So, what exactly is a footing? It is the lowermost part of the building foundation, and is built inside the ground. It is built of resting on the hard and compact soil in the deeper layers of earth. You must be wondering why footing is so important to the building structure. The footings are the final structural elements, which transfer all the downward dead and live loads from the superstructure into the soil below. These loads travel through the structural elements, like beams, columns, slabs, etc., which have limited area of cross-section. The footing finally transfers them to the soil, which has unlimited large area, thereby reducing the load intensity to diminish the pressure on the soil. This efficient transfer of loads prevents the vertical or lateral movement of soils in buildings. This also resists settlement and generation of lateral loads. Let us now take a look at the nature of a footing. The load on a footing may be a point load, traveling axially or eccentrically through a column. Or, it can be a line load, in case of a load-bearing wall resting on a footing. Footing, being a slab, is also a flexural member. Upon loading, the bottom fibers undergo tension, and the top fibers undergo compression. Usually, footings are made of concrete, to resist the compression. Reinforcement bars are used to take up the tension. A slab may be reinforced for flexure in either one, or both directions. Let us now look at the reaction from the soil, based on the loads on the footings. When a column load P is applied axially on the centroid of the footing, a uniform pressure is assumed to develop on the soil surface below the footing area. However, the actual distribution of the soil is not uniform. It depends on many factors, especially the composition of the soil, and degree of flexibility of the soil. In cohesion-less soil, the soil pressure distribution is more under the column area. Whereas, in cohesive soil, the soil pressure distribution is more at the footing ends than at the central column area. If the load does not act axially through the column, but applies eccentrically, the soil pressure distribution varies. When eccentricity is less than 1/6 of the width of the footing pressure is distributed in a trapezoidal shape. When eccentricity equals to 1/6 of the width of the footing pressure distributes triangularly, with zero pressure at one end of the footing. Whereas, the soil pressure is distributed in a triangular shape, with a portion of the footing of zero pressure, when the eccentricity exceeds 1/6 of the footing width. The resultant of footing pressure, R, coincides with the column load, P. Now, the loads in a structural member induce stresses. These stresses are due to different loading conditions, boundary conditions, and geometry. Now in design of footings, elements are designed to resist the different modes of failure. Shear failure occurs when inclined cracks form in footings, due to flexural and shearing stresses. This shear can be of two types: one-way shear and two-way shear. In one-way shear, the behavior is similar to that of beams, and hence, it is also called beam shear. In this case, the footing bends in only one direction. The critical failure section is along the length of the footing, at a distance d from the column face, where d is the effective depth of the footing. Two-way shear is also called as punching shear. When the total shear force exceeds the shear resistance of the slab will be pushed down around the column. This can be viewed as the column being punched through the slab. The shear stress acts around the footing, and the footing bends in both x and y directions. The critical failure sections in a particular direction are at a distance d by 2, where d is the effective depth of the footing. The shear force and moment in a footing are analyzed along both directions, longitudinally and transversely. Longitudinally, the footing acts as an upward loaded beam, spanning between columns, and acts as a cantilever beyond the columns. Using statics, the shear force and bending moment diagrams in the longitudinal direction are analyzed, considering the footing as a cantilever beam, from the face of the column to the edge of the footing. The footing is also subjected to transverse bending, and this bending is spread over a transverse strip near the column. This is the general reinforcement layout in a footing. In a two-way footing slab plan, the flexural reinforcement extends in both directions, and is provided across the full width of the footing. The shear reinforcement is also laid in the vertical section, where it is connected with that of the column. With this, you understand the basics of a footing, and its behavior under loads. In the next video, you will learn about design of footings. Thanks for watching.